So I'll be talking about quantum codes. I'll be starting out by giving a little introduction to what a quantum code is, classical and quantum linear codes. And the introduction might seem like this is some very complicated algebraic object, but then I'm going to show how you can just go draw pictures. Let's see, how do I get the... go draw some pictures and sort of interpret this in a completely geometrical aspect. And then I'm going to get to the new part of the work, which, oops, still not used to the buttons on this, which will be a way of trying to get quantum codes that have better parameters than known codes. As was mentioned, the best known parameters for quantum codes in terms of distance and so on when you restrict to low weight checks are much worse than those known for classical codes. Get to some technical results if I have time on how you prove this, which may be of independent interest classically in terms of some results on random lattices and then some open results. So we've heard before what a classical code is. I think most people know it. But let's talk about a classical linear code. So you have some message we'll talk about over bits, and it's some vector over bits. And let's say there's a k-bit message you want to send, and you encode it by a linear transformation into some larger n more than k bits. So you go from k to n bits, and the image of this linear transformation, the allowed vectors, the code words, one way to describe them will be the ones that obey certain constraints, parity check constraints. The number of constraints you need is the difference between n and k. And an important parameter for the code is the distance of the code, the distance between them, and that's the minimum weight of a vector that obeys all these parity checks. So that's what a classical code is. I want to rewrite it in a way that will be useful when we talk about quantum codes as a so-called chain complex. So this is just some notation that's used. C1 is a vector space. In this case, this will be this n-dimensional vector space of possible things you can say. And then this notation means that this operator partial 1, we call it a boundary operator, is just a linear map from this space C1 to some other space C0. So it just says we have one space, another space, a linear map between them. And the code words are going to be the vectors v and c1 such that this linear map on them vanishes. So this is just a way of saying that there's parity check constraints, and so we have two spaces and a map between them. And as an example, you could think about a repetition code. It has two code words, 0, 0, 0, and 1, 1, 1. If we talk about a repetition code encoding one bit into 3. Has two parity checks, for example, that the first 2 bits and the last 2 bits both have the same parity. And the number of encoded bits will be the difference between the dimension of this space and this space, assuming that all the constraints are non-redundant. So that's a classical code. Now, what is a quantum code? I'm not going to go into all the background of quantum coding theory, but roughly you need 2 different classical codes at once, because you have to send some message, and then you have to worry about correcting possible flip operations of bits, and then you also have to worry about correcting dephasing operations, where the bit is left the same, but the 1 picks up a different phase from the 0 bit. So you need 2 different codes. We call them correcting x, which is bit flip errors, and z, which is phase errors. And these 2 codes, one correcting one, one correcting the other, their parity check matrices have to commute with each other so that you can simultaneously measure the checks of both codes. So how do we write this? We write this again as a chain complex. So this means there's 3 spaces, C2, C1, and C0. The middle space, C1, is going to be where the messages live. This is going to be n-dimensional, which is the number of qubits that we send. This operator, partial 1, this boundary operator, will encode one of the constraints. It will encode, let's say, the x constraint. So this will be a map from C2 to C1 to C0. And then this other operator, C2, will encode the other constraints, the z constraints. And you should actually think of it sort of, it's the transpose of this operator, grad 2, is a map from C1 to C2, and that encodes the other constraints. And the fact that the 2 constraints commute is that if you take grad 1 of grad 2, this is just 0. And this is the defining property of a chain complex. When someone in math says it's a chain complex, they just mean you have a sequence of vector spaces and linear maps between them. And when you compose the linear maps, they vanish. So a quantum code is a chain complex like that. So it's 3 vector spaces and 2 linear maps. And the number of bits is the dimension of C1. The number of bits you encode is the dimension of C1 minus the number of constraints, which if the constraints are non-redundant is this and this. Now, when I talk about distance of the code, it's a little bit harder to explain. So really, what is a code word? A code word is, again, something such that this constraint, say, partial 1 vanishes on it. So it's something that's in the kernel of this, something such that partial 1 vanishes on it. But it's up to the other constraints. It's something such that this partial 1 vanishes up to stuff that's in the image of partial 2. So these are the code words. They're stuff in the kernel of partial 1 mod the image of partial 2, and this is called the homology. And the number of encoded bits, really, when you take into account the redundancy of constraints, is the dimension of this space called the homology. The distance of the code is the minimum weight of a vector that's non-zero in here. So meaning it's the minimum weight of a vector such that partial 1 of it is 0, but it's not the image of partial 2 of some other vector. So it's something in C1 its boundary vanishes, but it's not itself a boundary. And we're going to draw pictures, so this is going to be a lot. If this seems algebraic and complicated, it's going to have some nice pictorial implementation. There's actually two distances for the codes, because there's two different codes, a z code and an x code. So one of the codes distances is this. This is the distance against one kind of error. The other kind of error, you replace everything by transpose, and when you replace everything by transpose, you put a co in front, so it becomes cohomology. So it's the minimum weight of a vector such that grad 2 transpose on is 0, and it's not in the image of grad 1 transpose. So you want both these distances to be large. The distance of the code is the minimum of these two. You want both of them to be large. You want to correct well against both errors. And the weight of the code, the weight of the checks is just the row weight of this grad 1 and the column weight of the grad 2. And we want that to be small. We want the weight of the code to be small. So that's a quantum code. Now this might seem like complicated algebra, and it might seem, how would you ever go construct these codes with these properties? So let's talk about how you do it using pictures. So this is a picture. I have some vertices. Here's a vertex, here's a vertex, here's a vertex. And then I have some edges between the vertex, so there's an edge between the vertices and so on. But I don't want you to think of this as a graph, because what I also want you to think is, here's a face, here's a face, here's a face, here's a face, here's a face. And let's say there's another face outside, so there's 1, 2, 3, 4, 5, 6 faces. And so it's something that you glue together with vertices, edges, and faces. They don't need to be, it's like a simplicial complex or a triangulation, but they don't need to be triangles. They can be any shape. You glue them together. And then for every face, you put those in a one-to-one corresponds with the basis vectors of this C2. So there's the dimension of C2 is just the number of faces. The dimension of C1 is just the number of edges. The dimension of C0 is the number of vertices. And then these operators, grad 2 and grad 1, are just the boundary. So the boundary of this is this edge plus this edge plus this edge plus this edge. Nicely, since we're working over F2, we don't need to worry about signs. Otherwise, I'd need to tell you the sign rule for this. And then the boundary of this edge is just these two vertices and so on. And because the boundary of a boundary is 0, this just miraculously automatically gives you the rule that you get a chain complex. So for example, you start with this face. Its boundary is this edge, this edge, this edge, this edge. You see that I've drawn a closed loop. And since I've drawn a closed loop, it's got no boundary. So this is a way to make quantum codes. A way to make quantum codes is draw pictures like this and glue together faces and edges. And when you have this, then you can start to interpret the distance as a geometric property of the code of your this is called a cell complex of your cell complex. Now, if you go through the calculation in this particular case, you'll find that I've written a quantum code that doesn't encode any bits. If you take this particular one, it's because this is actually, since I treated everything outside as a face, this is really taking a sphere and drawing a picture on a sphere. You can imagine that I've sort of taken the edge of the slide and compactified it at infinity, and I've gotten a sphere. So I haven't encoded any bits. So let's say we want to encode some bits. Here's a way to get 2 bits, which is to take a torus. And you can see some fine cell structure on here. So there's like little square cells that I've put on the torus that go all the way around. And if you do this, this will encode 2 bits. How can I see that I encode 2 bits? Well, are there vectors, which a vector will be a sum of edges. So it'll just be a choice of edges that are closed. So it's a sum of closed loops on this torus, but are not themselves boundaries. Well, one is just go all the way around the torus that way. That's closed. It's a closed loop that goes all the way around, but it's not a boundary of anything. If you just drew a little loop that went around in a circle right there, somewhere on the torus, that would be a boundary. You could shrink it to a point. But you have 2 loops, one that goes that way and one that goes around the other way, and so it encodes 2 bits. So that's a way to make a quantum code, and this code is called the toric code. It's a famous one. Now let me zoom in on the torus. Let's just do a much more coarse-grained cellulation with just a few of these instead of that previous one had hundreds of squares on it. Let's take one with a smaller number. So again, this you should think of this as just a way of putting this cell complex on a torus. So I've got here's a face, and what this notation means, I've got this edge coming off here. I drew these dotted lines to indicate we're going to take this edge and join it over to here. So the right-hand side of this edge will join and attach the left-hand side. The right-hand side will attach here, and so on like that. So just take this thing and attach the right to the left and the top to the bottom, and you glue it up and you get a torus. And here's a picture of that thing that goes all the way around, one of the two ways of drawing some vector that's non-trivial. And the code distance is just the length of this vector. So the code distance is just some property. It's the shortest homologically non-trivial cycle, or cohomologically non-trivial cycle. And so you see this is the shortest way to do it. So it has 1, 2, 3. This one's a little bit longer, 1, 2, 3, 4, 5. So you should do it the shortest way that you can, and that's the distance of the code. You can also play this game in higher dimensions. So you don't need to just draw faces, edges, and vertices. What you can draw is some higher dimensional things. So you could take, for example, a 3-dimensional object and draw cubes on it. And then you have cubes, faces, edges, and vertices. And then you could choose any of them to be your qubits. So you could say, I'm going to take a three-dimensional thing, I'm going to put three-dimensional cubes on it, and then I'm going to put my qubits on the faces, which are the two-dimensional parts, and then the checks will be the three-dimensional part and the one-dimensional part. So the qubits will be the q cells for some q, say 2, the faces, and then the z checks will be the 3 and the 1 cells. So then, again, it's just this rule of the boundary. So then for every cube, there'd be a z check, every edge there'd be an x check, and every face there'd be a qubit. So here's a picture of sort of a possible set of qubits. In that case, you see some three-dimensional thing join the front to the back, left to the right, top to the bottom. You get a three-dimensional torus, and you see some little faces that represent these, some possible set of qubits. This one does not have vanishing boundary. It does not have vanishing boundary. As you can see, you can see an edge there. So it's not what we're looking for, but it does have vanishing co-boundary, it turns out. I've actually drawn a picture here with vanishing co-boundary. So it's a possible X-type logical operator, not a possible Z-type logical operator. There's the two types. And it's much easier, if you want to think about the co-boundary, to dualize it, and what you actually see is it turns into the straight line. You can Poincare dual and interchange q and n minus q. So that might be a little, if that seems weird, just think that we're mostly going to work in half the dimension. Q is n over 2. And in that case, everything you can just think of as boundary. You're looking for half-dimensional surfaces that are closed, they have no boundary, and are also non-trivial. And that's what tells you your code distance. So the code distance is still a geometric property. It's just the least area of these things. So you're just trying to draw interesting manifolds with where the least area non-trivial thing is big. How am I on time? 6 minutes? Wait, have I taken 15 minutes?
No, wait.
16 minutes. So I just wanted to make sure.
Let me just.
Okay. Okay, I'll keep talking, you tell me. And then the weight of the checks is roughly the dimension, because you think that, well, a cube, for example, an n-dimensional cube has n, or rather 2n faces. So it'll depend exactly how you cellulate it. But as the dimension goes up, the weight of the checks goes up. Okay, so best known parameters. What's the best that anyone has done? We're just going to focus on k.
You should be finishing at about 12:05.
Okay. Best known parameters. Classically, so k, number of encoded bits, d, distance of the code, and w, weight of the checks. You want k high, d high, w small. You would like other properties like efficient decoding. The weight is, in a sense, a proxy for efficient decoding. Small weight will hopefully help do it. And it's also useful quantumly because you have to have some circuit to measure them, and smaller w makes it easier to measure. Classically, you can do as good as you want, essentially. K can be order n, d can be order n, and the weight can be order 1. Quantumly, if you want the weight of order n, the best known just barely beats square root n. Just barely beats by some square root log n. It's quite a complicated construction. If you want to get up to distance theta n, the smallest known is weight order square root n. So no one has kept the weight at 1 and beaten the square root barrier. This seems to be some barrier. Now, why should square root be a barrier? So the intuition, think about just a n-dimensional torus, all the sides orthogonal, length L on a side, and put the qubits on the q cells. So now, this non-trivial operator, you could just have a plane. So you could have a three-dimensional torus, and you could have some non-trivial operator that's a plane in 2 dimensions. And the weight of this operator is just L to the q, and for the dual one is L to the n minus q. And the way to make these as big as possible, as q goes up, this one goes up in weight and this one goes down in weight. The best thing to do is take half-dimensional, and it's optimal at square root distance. And you have to work a lot to beat that. So how can we do better? So let's look in 2 dimensions. And here's that particular torus I drew before. That's the one I drew before, and how you join up the edges. And how can we get this cellulation on the torus? Well, a torus is the whole plane modded out by some lattice of translations. And there's an easy way to think of cellulating the plane. You take squares, or hypercubes, and you cellulate the plane by that. So here on this side, I've drawn the whole infinite plane cellulated by these squares. And this is this lattice. These big circles are the points in the lattice I'm modding out by. And that gives you a way to get the plane. And then this shaded region is just sort of a region that's big enough to contain one unit cell of the lattice. Now suppose you used a different lattice. Instead of a lattice where it had some orthogonal basis vectors, consider a lattice here with some non-orthogonal basis vectors. What you find then, this is fewer qubits. The volume of the cell is smaller. Things now join up in a funny way. The top doesn't join to the bottom, but rather the top joins to the bottom with a shift, because when you move up and up, you find you're not back where you started, but you actually have been shifted over too. So there's some funny shift when you join the top and the bottom. But it has the same distances up here. It has the same distance because the minimum distance between lattice points using the Manhattan metric is the same. So you can change the lattice, and you can gain a tiny bit in 2 dimensions, not much, but a tiny bit with a cleverer lattice. As you go to higher dimensions, you can gain a little more if we stick at q equals 1. The reason is that there's high dimensional lattices where the shortest lattice vector, in the lattice compared to the n through to the volume of the lattice goes up by the square root of the dimension. So you can gain a little more by choosing some lattices. This isn't much because the dimension is only going to be log of n, so that's really very little gain. And this is only worries about the one of the 2 distances, and we really need to worry about both distances, the z and the x distance. So I don't want to talk about q equals 1. I want to talk about q equals n over 2, and here we're going to see we can gain a lot. So you look at high dimensional lattices, and this is the key idea. You look at high dimensional lattices, you look in half the dimension, and you can come up with high dimensional lattices which have the following property. There's this invariant called the Rankine invariant listed here. It's a property of the lattice, the dimension of the lattice, and this q that you're looking at, which is, so a natural thing for lattice is shortest vector. What's the shortest vector in the lattice that's non-zero? A generalization of this is this Rankine invariant. Pick q vectors that are all in the lattice that span a non-zero volume. The determinant of the span by them is non-zero, and look at how that volume compares. The volume spanned by those vectors compares to the volume of the whole lattice appropriately normalized to the raised to the q on n, so it's normalized, and this factor of 2 is for historical reasons. So it's roughly the area of, you take a hyperplane in the lattice, not a single vector, but a hyperplane that's spanned by lattice vectors, and how does that compare to the volume of the lattice? And it's known, this is paper in crypto, that this is another interesting hard lattice problem, like the shortest vector problem. It's known that you can make this really big. So you can sort of, just to get a rough intuition, you can have one vector that's square root n longer, but you can make it so that actually 2 vectors in the lattice have to span a big plane of order n, and 3 vectors have to span a cubic volume that's of order n to the 3/2, and so on. And you can make it such that there's a lattice that any n over 2-dimensional sublattice has an n to the n volume compared to what you would think. It's really big. So these hyperplanes are huge. So the idea of this is, let's look at this toric code on such lattices with large Rankine invariants. These things are known. A problem is it's not known how to cellulate them, because this is a completely non-constructive thing, and it just gives you lattices with some basis vectors that are real numbers. So what I want to do is I want to stick to integral lattices. I want integral lattices so I can cellulate them just as I did before by using hypercubes. And we don't really know if this hyperplane is the best thing. So this is the geometric conjecture. So the geometric conjecture is that there's some constant so that this n over 2 systole just means least area, half-dimensional thing, that's the geometric term for it, is lower bounded by this area of the hyperplane up to something that grows at most exponentially in dimension. So it's the conjecture. How should we get some intuition for this? Well, let's look at 2-dimensional things embedded in a 3-dimensional space. I know that's not half-dimensional, but this is what we can draw. So just as we can get our lattice by taking the real space, our torus by taking the real space and modding out by the lattice, we can take something that lives in this torus and extend it to all of space by translating it by the lattice. So if you had a plane on a 3-dimensional torus, it turns into stacked planes in 3-dimensional space. So this is some low area thing. And you can prove, in fact, that those are the best ones, at least in 3 dimensions. This conjecture is definitely true. Instead, if you had some other crazy structure, it would turn to some really weird n-fold periodic structure in higher dimensions, maybe something like this, one of these triply periodic minimal surfaces. This one's not actually homologically non-trivial. There are no such examples in 3 dimensions, at least. The conjecture is true in 3 dimensions. But this just gives the idea, like, is there some crazy surface along these lines that beats what you can do along these lines when you go in higher dimensions, and beats it by a lot, a super exponential factor? If this conjecture holds, this is the main result in the paper, then you can get almost linear distance. You can get n to the 1 minus epsilon for any epsilon, weight log n, and the construction is a family of toric codes on these lattices. So the main technical tool to do it, how am I on time again? Okay. So the main technical tool to do it is to come up with these integral lattices with large Rankine invariant. They turn out to have essentially as good Rankine invariant as those other non-integral ones. There's a great paper, I love the title, Lattices Which Are Good for Almost Everything. It turns out there's one more thing they're good for, that they have large Rankine invariant. The way you do it is you take a linear code over some prime. The lattice points are the vectors that fall in the code mod that prime, so you just extend it to it. And so the construction is sort of funny. You start with a linear code over a prime. You go to one of these lattices, they're called LDA lattices, and then you take the toric code over that, and that gives you a quantum code. essentially the way you prove the thing on this. Well, how would you prove a lower bound on the length of a vector in a random lattice? What you might do is such a random lattice. What you might do is you just first count how many short vectors there are, and then you ask what's the probability that such a short vector falls into the code, and that's a very simple probabilistic method proof to estimate the number of short ones. And that's how you would prove that there's no short vectors in these particular lattices. There's an extension of this where you count the number of, you sort of work one at a time in those vectors v1, v2 up to v half dimension. You have to put them in some canonical form. And then you use first that proof to show that this one is unlikely to be small. Then with the generalization of it, you can show that this one is also unlikely to be almost parallel to any of the previous ones. So there's a generalization of that proof. So I'll quickly just mention some other results and open questions, and then I'll close. You can construct some quantum locally testable codes in this with new properties. And you can get rid of this log n weight. This construction wound up giving a log n weight, that the weight of the dimension little n got large, and the dimension little n was log of the number of qubits, it turns out, in this construction. So the weight of the generators wasn't quite O of 1, was weight log n. So there's a subsequent paper I wrote that shows how for any code, if the weight is log n, you can turn it to O of 1 just costing a polylog in the distance. So you can do that. So open questions, obvious open question, is the geometric conjecture true? If not, what are these crazy surfaces in high dimension that violate it? Would the conjecture be easier to prove instead of on these particular random tori, but on some other tori? For example, if you took like a Barnes wall lattice or some other lattice with some nicer properties, it turns out that its Rankine invariant is not good enough to actually give a non-trivial bound unless you find a better cellulation. But perhaps on some other tori like that, it might be easier to prove. And also, can you construct large Rankine invariant tori in a deterministic way? So, thanks.
All the speakers?